you for basically inviting me. I'll be talking about regular games, and so this is a what I don't know. Okay, a joint work with Zihui Liang. So he's a PhD student. He's a second year PhD student. Basically, it's his work. So in a sense, it's his work. He provided many algorithms here. And Mingyu, he is in my lab, and he was a student of Andrew Yao, and now he is the chair of the Theoretical Computer Science Committee, Chinese Federation of Computer Science. So a very, very supportive person. And he does parameterized complexity. I don't know what's happening. Thank you. Yeah. Okay, so the plan, I'll basically, most of you know the definitions, but some probably not. I'll go through basic definitions. I'll talk about the sizes and parameters of the games. And then it's sort of our results. So it's a general methods of looking at all these games. And I'll talk about Mueller games, colored Mueller games, Rabin and Street games, Mueller games, and McNaughton games. And we put the paper into archives. And we got the results probably about a year ago. So I checked them when we were working on that. So in details, probably now I might not remember certain details, but let's see how it goes. So arena, so I'll just go to the basic definitions. So the games are played on arenas. Arena is bipartite graph. Only V0 is the play 0 nodes, and V1 is the set of play 1's nodes, and E is the set of edges between V0 and V1. And one condition I put on E, just for convenience, I assume that every node has an outgoing edge. So again, the play, obviously, so you have a token. Token is placed on a position V, and let's assume V is at play 0's position, that is belongs to V0. Play 0 moves the token along one of the edges, and the token goes into play 1 position. Play 1 does the same, and it continues on, and they produce infinite path. And so a path, so that's a definition of play. Play is starting at V0 is simply an infinite path. So you know all these things. And the winning is determined in terms of sort of recurrent behavior of the play. So you're given a play, and because the graph, I assume that the graph underlying arena is finite, you can collect all the guys in the play that appear infinitely often, and this is called infinity set. And the winner is determined by the conditions put on this infinity set. So, and I'm going to go through several of these winning conditions. So, colored Mueller game. So you give an arena, and you have a function that associates with every vertex or every position a color, and you split the set of 2 to the C, so that's a collection of all subsets of C, into 2 sets. F0 is a collection of subsets. F1 is the complement of it. So that's, and you look at the play, and you say that play sigma wins if the infinity set, you look at all the colors that appear infinitely often in the play, and if this infinity set of the colors is in F sigma, then play sigma wins, or play sigma wins. So that's a colored Mueller game. So Rabin game is given by arena and a set of pairs, and the K, the number of pairs, is called the index of the Rabin set, of the Rabin winning condition. So these are the subsets of V, and play 0 wins if there is a witness, there is a pair such that, so the left side of the pair is visited infinitely often, while the right side of the pair from some point on will never be visited. So otherwise, play 1 wins. So this is the Rabin game, and street game is the opposite of play 1 game, of the Rabin game. So you're given pairs, again, the K index, and play 0 wins if the opposite of what to Rabin happens. That is, for every I, whenever rho visits UI infinitely often, rho visits Vi infinitely often. So these are three, yeah.
Why the asymmetry? You have colors for Mueller, but you don't have color for Rabin and Street.
There is no symmetry here, but here there is symmetry.
Well, there is also infinite, or the color.
So here you have a symmetry, here.
No, but it's both, all of them are about infinity, but in one case you look at the infinity of colors.
Yes, you mean you're talking about colored Miller games, right?
You're looking at the color. Yeah, why I don't understand why you need the color for Mueller game, but you don't need color for Rabin and Street. You could have worked directly with Mueller game without color. What does the color add?
I'm not sure I understand your question.
And not only that,
it's
not only that, it's even color with you. That makes the game much more complicated, spelling color with you.
I mean, these are standard definitions, right? I mean,
okay, yeah. Okay, we'll see.
We'll see, yeah. Okay, so, I mean, Rabin games you can transform into the colored Miller games, and Street games you can transform them into. So McNaughton games, again, you can transform the Miller games or colored Miller games. So the McNaughton game is given by a collection, so arena, and you have a specified collection of nodes, W, and you collect a bunch of subsets in W, so you call it F0, and these are the winning sets for player 0. So that is, take a play, you look at all the nodes which appear infinitely often but belong to W. Mm-hmm. So if it is in F0, then play 0 wins, otherwise play 1 wins.
Can we just stop for a second? Apparently, from people who follow told me that the camera seems to go out of focus very frequently for the current talk, but this was not the case for the earlier talk, so maybe, okay, I informed. Thank you.
Okay. Okay, yeah, so continue on. So
Bakh fading in and out. I thought it was just my vision.
Okay, so the Mueller games are the same as McNaughton games, in which case W is equal to V. So I'll just now go through all of these games and present our results. I'm not going to go through the proof. Oh, before that, I want to make a couple of things clear. So when you're given a game, you can think of it, you can representation of it. So two ways to think about it. One is, so just the number of vertices plus the number of edges. That's the size of the input. But the other is you take into account the winning conditions. So if you take into account winning conditions as the size of the input, so then the size for Mueller games, for instance, McNaughton and colored Mueller games, is going to be V plus E, and you need to record the winning sets. So it's going to be, it can be exponential. But for Rabin and Street games, so the size can be 4 to the V, because you're talking about the pairs of subsets. So potentially they can be quite large. And I call C a small parameter, so the C is the color, because the size of it is bounded by V. And W, it's in McNaughton games, I also call it small parameter because the size of it can be bounded by W, but the size of K, well, is bounded by 4 to the V. K is the number of the index. So, okay, so potentially, so this guy can be big, so I call it the large parameter, potentially. So we have 2 small parameters and 1 large parameter. So basically, when you talk about basically running time, you need to be explicit which size you're talking about, this one or this one. So we all know that the games are determined. So you can partition the arena in 2 parts, W0 and W1, such that X belongs to W0 if and only if play 0 wins, and Y belongs to W1 if and only if play 1 wins. And so solving a game means to do 2 things. One is you want to decide who wins, that is, you want to find out W0 and W1, and let's call it decision problem. And the second objective is you want to extract the winning strategy for the winner. So this synthesis problem. So typically, like if you look at all the literature, what people do, they pick up an instance of the games, either Miller games or colored Miller games or Rabin games or street games. They look at the decision problem and then also talk about the synthesis, typically. So they focus on a specific class of games, right? So, and I'm not going to do it. So we try to find the general methods. So we focus on just decision problem. So here are the results about colored Miller games. So again, at the top, a definition of colored Miller game. So these are the best known results. So the running time, so there is an algorithm that solves the colored Miller games with running time c to the c. So this is the colors. So space is c factorial with some polynomial degree, with some degree, constant degree. But you can also solve the problem, so recursively, the folklore result. So if you do the induction on C, so you can show that, so the colored Miller games can be solved in this time, running time. So, and we design an algorithm. So basically, basic idea is we use the dynamic programming methods, and we design dynamic programming algorithm to solve these games. And as far as I know, so let me know if I'm mistaken. So I've never seen in the game theory community the dynamic programming algorithms that solve these games. So this is probably the first time when we use the techniques of programming, dynamic programming methods to solve the game. So, and this is what we have. So we have, so sort of if you look at this, we're not dependent on C. So over there, so the focus is on C, but here, so our running time is 2 to the v, C times E. So this dynamic programming algorithm, again, 2 to the v, v times E. So the difference here, I think, is in space. So here you're multiplying 2 to v. So the sizes now here, it doesn't matter because you have 2 to the v here. So which representation of the sizes you pick up, it doesn't matter. Okay, so we have this. And recursive, so it's now basically if you look at this now and you compare C to the C, so basically what you need to do is you need to understand, we need to understand what is the difference between exponentiation and C to the C. When is it the case that we're better? Right? That's a natural question. So which one is better? And when is it better? Now, if you look at the recursive algorithm, our recursive algorithm, so we already win here. So if we do the recursion, so that's C times E, so V times E, C to the C. C to the C is replaced by C factorial. So C factorial is already better than C to the C. And V to the C, it's the same as this. So it's that we have. Now, I would like to say, how do you compare this C to the C with 2 to the V? So, here's the comments. So if the size of your arena, if the size of C is greater than V log n is the size of V in number of vertices. So in particular, so if C is greater than half of V or any fixed fraction of V in particular, right? So we're better. So our algorithm is better. And this is, in a sense, like a good condition on C. So C, recall C is a small parameter, right? But also very interesting, there is a result from here which says colored Miller games cannot be solved in this time on the ETH hypothesis. So now, if you look at our algorithm, we are saying that we're actually doing in exponential time. So what it actually means is, so we are refining this result. I'll talk about it a little bit more. So we are basically, so one motivation you can think of, the result is a motivation on its own. That is, we're saying that we are basically improving the impossibility result. I'll talk about it in the next page. So the spaces are better than the best algorithm. So this is the best algorithm, and this is our space. Under the condition then C is greater than V log n.
Can you be a bit clear about are you going to talk about what you mean by dynamic programming?
I mean, you pick up. I'll talk about them at the end of the
I'm
talk.
not quite sure what I mean, because I mean there are various fixed point characterization of these games. Is this the dynamic programming?
I'm not sure. I don't know, Moshe. So the fixed point characterization.
I mean, there are parity game solver that are based on a essentially fixed point algorithm.
So what we do. So there is a concept of full win. I'll give the definition of full win, and we exploit that quite significantly. And we start basically run through all subarenas. That's where exponentiation coming from, and collect all the subarenas where play 0 fully wins and play 1 fully wins, and build up strategies from that. I don't know. That's basically dynamic. That's where dynamic programming idea comes from. You building small games and building up the solution.
Well, I'm just thinking that the parity game, symbolic parity game solver, in some sense, do dynamic programming on the parity tower. Okay, I mean, I don't know if you consider dynamic.
No, we don't do the parity tower. So we run through all the subarenas. So in a sense, we're running through subarenas. So
I see. Okay.
But it's, I mean, I'll talk about this a little bit more. So all the previous algorithms run in super exponential time if you take into account the parameters, right, into account. So we are polynomial. So here's the ETH. So this is value of C from 0 to V divided by log V. So over here, we do exponential time algorithm. So now, if you look at our proof, so the proof here that ETH is impossibility result about using the ETH, actually, what happens is over here, C to the C is smaller than 2 to the V. So that's where ETH is applied, actually. Over here, we don't know what happens, whether there is a exponential time algorithm between square root of V and this, so we don't know what happens. So that's basically sort of clarification of how ETH is applied. Okay, so Rabin and street games. So these are the best known algorithms. So we have V to the K, K factorial. Here G, I'm not sure the size. Size is the standard, V plus E, right? I think it's V plus E. But maybe you need to record everything, I don't know. So V plus E, yes, okay. So, and very recent result, so which is 1 plus, so this K plus 1, I think, no, K factorial, so this is very recent result. So. And again, so we did our algorithm. It's our algorithm, what it does, it actually takes Rabin game transforms into Mueller games. And then using the solution for the Mueller games, you come up with this algorithm. So you have K, so we removed factorial totally. So KV, 2 to the V, again, exponentiation instead of K factorial. But the space, our space here is bigger. So that's a little bit negativity in our result. So here the space is the linear, but here is exponential. So it's explicit representation. But our recursive algorithm is better. Well, I'll explain a little bit. So better than this, again, you have K here. So, but V factorial. When I say better, so better means this. In terms of both, in terms of time, both our DP and recursive algorithms are better than the previous algorithms. When K is between, so K, remember K is a large parameter. It can have very big values. So from 0 to K is very small, and the rest is very large. So we have better algorithm. And again, so there is ETH results, which says Rabin games cannot be solved in this time. Okay. So, but we improve this by saying that if K is greater than V log V, then we can solve in this time, in exponential time. So that's just like in the previous case. And again, our algorithm is the first exponential time algorithm that decides Rabin games. When Also, I want when k is between v and 4 to the v, our recursive algorithms is better. So you don't need. So better in terms of time and space. So I want to talk about this as well, Mueller games. So you're given a Mueller game. So Florian Horn provided an algorithm that runs in polynomial time if the game is presented explicitly. That is, you explicitly write down all the winning conditions. So we studied his algorithm 1.5 years ago. And it's a beautiful algorithm. So it's basically a reduction type of algorithm. You take a Mueller game, and slowly you start taking out the winning conditions. Sets f, sets, let's call it x from f0. You take it out, but you repair the damage by extending the graph. So if f0, and you do the f0 times. So you get the game which becomes very large, depending on which is equivalent to the size of f0. But it turns out his algorithm is wrong, so induction terribly fails. So, and algorithm is correct, algorithm is beautiful, but proof of correctness is wrong. Right. So the induction fails in his proof, and non-trivially. So like people worked on it, and I know a bunch of people worked on it, tried to understand where the mistake was, and it's not easy to detect. What else? What can I say? So his method doesn't work. So we provide a totally new method, and showed that his algorithm works. So we provided this algorithm in ESA, what is it? European Symposium of Algorithms. So, and our algorithm is this. Again, we use our algorithm 2 to the v. In particular, when the size of the winning set is greater than square root of v, we're better than this. So we submitted this paper to a couple of conferences, and the referees, one of the referees was that natural examples. Where are the natural examples where f0 is large? Right. So my answer is I don't know, but I can give one very simple, in a sense, natural examples in my view, is the following. You take arena, and you pick up a subset at random. So for every vertex, you toss a coin. If 0, you throw it away. If it is 1, you put it in. So, and that's going to be your set. Let's call it x. The size of x is half of the cardinality, expected size. And you declare all subsets of x to be the winning condition, winning sets. That's sort of a natural definition of Mueller game. And in that Mueller game, the size of f0 is greater than exponential. Well, it's about exponential. So that's a natural example. For those type of examples, we get the polynomial time algorithm. And this one, if you run as equivalently parallel with these two, then you get a good running algorithm. So finally, McNaughton games. Again, we have exponentiation 2 to the v, dynamic programming algorithms. And when the size of w, the special sets, special states, is greater than v divided by log n, then our algorithm is better. So I'll come back to this. Now, the question is, why do we have such improvements? So here's my take on it. So now, if you look at most of these algorithms that we worked on, so we take into account C, W, and K. So the parameters are part of the input, and we want to basically design algorithms based on those C, W, and K. And when these parameters move from very small for me is log or log, to reasonable, so to reasonable sizes, then you get these types, the running times, right? And these are like not efficient. So, and therefore the idea was that it's better to run the algorithms that go through all subsets. When you go through all subsets, it's exponential. And exponential beats these things when k is reasonable size. So, and of course, this is like I'm simplifying things. You need to do a lot of work to do this. To do 3, you need to do a lot of work. Okay. And now I'll briefly explain what we did. So in that, so here's a definition. So this definition has been known, but not given, and it's been used in I think in parity games. Like, so you given game and you say that play sigma fully wins if a winning set is V itself. Right, so if you want to solve a parity game, solving a parity game is equivalent to solving whether a given player wins fully. So if you can solve the parity game under the assumption that you know that one of the players wins from any node, it's equivalent to solving a parity game. So, and this turns out to be sort of conceptually and technically the main notion. So we use this all the time in our algorithm. So this definition. And so attractor set, I'm not going to, well, you're given set X, you're given arena, and play sigma wants to get into X. And you can, so the collection of all nodes where play sigma can get into X is called the attractor. You can compute it in linear time. So here is the lemma. So this is basically recursion. So using this lemma, you can do the recursive algorithm. But the key here is 1. Right? So what it says, it's basically characterization of what it means for player to win fully. So it's a Mueller game is given, a Mueller game, colored Mueller game. So play sigma 0, 1 wins fully if and only, okay, so it's if and only if for every color C prime, either the given player can get into the nodes of colored C prime from any position, or player sigma wins. You look at the attractor set of the given color and look at the complement, and the complement is going to be, what is it? It's going to be a trap for player sigma, and if player sigma wins the trap. So it's a full, so, and this basically player sigma fully wins G if and only if this condition is satisfied. And we use, in dynamic programming algorithm, we use this property all the time. Okay? But the lemma itself is used in the recursive algorithm. And so to run the dynamic algorithm, you need to do this type of property for the opponent. And it turns out you can do it. So here's the, so it's basically, I call it trichotomy lemma. It's relatively simple. It characterizes when player 0 fully wins, or player 1 fully wins a given game, or none of them fully wins. Okay, the first one, player 0 fully wins if for every C prime, player 0 can get, for every color C prime, player 0 can get into a vertex of color C prime using the attractor strategy, or player sigma wins the trap outside of attractor. Otherwise, on the condition the player doesn't win, so that's a key point. Under the condition player doesn't win, very similar thing happens for the opponent. Otherwise, for every node, instead of now every color, I'm saying for every node, so you look at the attractor, whether the opponent can get into V from every point, or the opponent wins the complement of the attractor. So this is full win condition for player 0. This is full win condition for player 1, on the assumption that 1 doesn't hold. If 1 and 2 doesn't hold, then none of the players win. And this is the key for dynamic programming algorithm. So we also use enumeration lemma for rabbinic games. So K, that's why you have K there. So if you have K subsets, and you look at all the subsets, if you want to enumerate all the subsets of V1 and all the subsets of Vk, what you can do is, well, you can do the brute force, then your algorithm runs 2 to the n k times. For every V, list out all the subsets. And you need to do it k times. So this enumeration lemma removes k. So in particular, note that k can be exponential, right? So we're removing k from here. So you can do that. And this is where basically we use, so this is used in the basic, you take Rabin game, transform it into Mueller game. And when you transform it into Mueller game, so we remove the dependence on x, on k in this way. So this is one definition. We call it KL. I was in Kuala Lumpur. And I was talking on Zoom chat with my student, and we were discussing how to compress Rabin games, and we came up with this condition. So you give an arena, and KL game is a set of pairs. These are the elements of the arena. These are the subsets. And you take a play, a player wins, play 0 wins a play if there is a pair UI-VI, UI-SI such that UI appears infinitely often, and the infinite set of rho is a subset of SI. And so the winning condition, so that this is the size of the winning condition. And note that what I want to do here is the k in the Rabin game, the k can be 4 to the v. The size of the k is 4 to the v, but here the size of the index is exponentially, is always exponential times smaller than 4 to the k. I say 2 to the k, max. So that's what you get. And then you can transform this in Mueller. So basically, so there is a transformation from KL games to Mueller games, and this time, and hence you can solve the KL games and the exponential time. And you can transform Rabin games into KL games in this time, and then you basically apply the algorithm that solves KL games, and that's why you get the running time of the Rabin for the Rabin and street games. So it's, I'll finish up with open questions. So we know that Mueller games can be decided in polynomial time. We don't know whether McNaughton games can be decided in polynomial time if McNaughton games are given explicitly. We don't know that. So this one, if you remember, for colored Mueller games, there is that bound where we don't know whether there is an exponential time algorithm for Mueller games, for colored Mueller games. This is the bound. It's an open question. And another interesting thing is so McNaughton games can be solved in this time. I don't know whether it is possible to replace this V with W. So if you replace this V with W, what it means is that ETH type of arguments do not work here. So potentially that means that you can solve McNaughton games in polynomial time if they're given explicitly. I think I'm done. So. I expect many questions.
So if you think about your dynamic programming, which essentially goes over arenas,
yes.
Can you try to do it symbolically? And then, each arena is kind of, in some sense, it would an algorithm, it will operate on all the arenas at the same time.
I haven't thought about it, Moshe, but I think it's a good idea to look into that. I haven't thought about it. So it's definitely one path to look at.
Is your algorithm always worst case complexity, or you can hope that once you take a game, then you, like Jelonka algorithm or whatever, you can hope that, okay, you hit worst case complexity only sometimes, and normally you are not exponential?
I don't know. I really don't know. It's a good question. By the way, good to see you, Igor. So yes. We go through arenas in a very careful way. So if you can control arenas, like if, then probably, so you can do better. Probably it depends on the arenas. I don't know.
Yeah. So this is a bit of a naive question. So you identify decisions and enumeration. Can parts of these be reformulated as decision or counting problems instead of just?
I don't know. Again, sorry.
Or parity games in polynomial time?
Okay, so I can be open. So I put these questions into my student, and the eventual goal is to attack the parity games. And I don't know whether these methods help. I have no idea. So it's, I think full win, it looks like a naive definition, but it seems it's a cool definition.
What is a cool definition?
Full win notion. It's interesting definition. Using this full, again, I go back, you came back to me. Let me look at so this one. I talked about this, and you take Müller game and you transform it into sort of exponential size. So the size of the game, where the size of the game, reachability game, the size of the game is equivalent to F0. So you're changing the arena using the notion of full win. So Zihui came up with a beautiful, extremely simple algorithm to solve these games. Very, very simple. You don't change the graph, underlying graph. You just look at the winning conditions and you extract all the information needed from there. So it runs in the same time, but it's very different algorithm, and it's a nice algorithm. And it's what I expect if Müller games can be solved, parity games can be solved in polynomial time, something unexpected, some kind of unexpected behavior like this should come up. Or, where is Marcin? Marcin. Or you need to do something dynamic algorithm, not dynamic programming algorithms, dynamic algorithms. So you basically take a parity games, trivial parity games, everyone is connected, and start removing the nodes or edges one by one, and analyzing that dynamic algorithms probably might, together with this type of things, might help. I don't know. So I think there is a polynomial time algorithm. Frank Stefan, my colleague, thinks that there is no polynomial time algorithm.
About quantum polynomial time?
I don't know. I don't know quantum computing, so sorry.
Any other question?
I have a question on behalf of Supratik, who asks, do any of these techniques help sharpen, improve lower bounds for the corresponding problems?
I mean, there is ETH results, right? So impossibility results. So that would be my answer. So for Rabin games and for colored Müller games, you have low bounds exponent, and we're getting that low bounds. We did the exponentiation. So that would be my answer, I think. But for McNaughton games, I don't know. So they might help.
Thank you on behalf of Supratik.
Yeah, thank you.
I think for parity and Rabin game, what we get in, for example, in synthesis is that the index is logarithmic in the size of the of the state space.
Yes.
So what happens here? I don't know that you have not specifically looked at this.
Good. I didn't. That's a fantastic question.
The logarithmic region to me is the most interesting region.
That's a fantastic question. So if you look at what is happening here, this is Rabin. Yes. The size of K here, I'm saying greater than or equal to the size of the arena, right? So So this is the condition. What you're saying is usually in typical examples where you have k is and logarithmic on the size.
Logarithmic in the
So
size of the arena.
that's a criticism for this paper, definitely. But what I want to do here is to say this. So take determinization process. So take non-deterministic Bakh automata with n states, n. So let's remember n. And then you determinize it into Rabin automata. When you determinize into Rabin automata, you have 2 to the n log n states, but your but the index becomes n plus 1. So
yes.
n and to the, so this is the size, but n is staying there. N is still staying there.
Yeah.
So you have n factorial if you want.
It's roughly n to the n versus n index n.
Yes,
so it's a little below logarithmic, but it's not doesn't get to the log region.
Yes, exactly. So
just maybe this little below logarithmic, maybe it helps. I don't know.
Yeah.
Okay.
Yeah, that's a good question. But what I want to say, when you apply then standard algorithm, you still have n factorial on top of 2 to the n log n. So so in that sense, that would be my answer.
Yeah. Any other questions? Okay, let's thank Bakh.
Okay, thank you.